Fair learning to rank, LTR, models are increasingly being deployed in decision-making systems with profound life implications. However, these models rely on sensitive demographic features, which are often protected by regulatory obstacles and privacy concerns. This paper investigates how errors in demographic inference impact the fairness performance of popular fair LTR strategies. The authors examine a spectrum of fair LTR strategies, ranging from fair LTR with and without demographic features hidden versus inferred, to fairness-unaware LTR followed by fair re-ranking. The authors conduct a controlled empirical investigation, modeling different levels of inference errors by systematically perturbing the inferred sensitive attribute. They also performed 3 case studies with real-world datasets and popular open-source inference methods. The findings reveal that as inference noise grows, LTR-based methods that incorporate fairness considerations into the learning process may increase bias. In contrast, fair re-ranking strategies are more robust to inference errors. The study highlights that fairness-aware strategies achieve considerable fairness even when working with inaccurately inferred demographic attributes, but fairness decreases as inference errors increase. Moreover, in a scenario where demographic attributes are missing, it is better to utilize a fairness-aware model that relies on inferred missing attributes than to adopt a fairness-unaware model that ignores the missing attributes, as long as inference errors are relatively low. The authors also observe that fairness-unaware models show increased levels of fairness when working with demographic attributes that had been incorrectly inferred, which can be attributed to candidate items being wrongly classified as members of the alternate group. The study emphasizes the importance of verifying the quality of inference tools and highlights the need for practitioners to proceed with caution when utilizing demographic inference in fair LTR strategies. The paper further discusses the importance of factoring missing data into classifier models for fairness in classification and regression tasks. It highlights the need for fairness in information acquisition, particularly in fair classification and re-ranking. The authors introduce fair ranking algorithms and describe how they compose these algorithms into a spectrum of alternate strategies for integrating fairness into fair learning to rank pipelines. They also present tools for inferring protected attributes and metrics for fairness and utility. The paper focuses on fairness-aware models, such as DELTR, which aims to reduce disparate exposure while maintaining accurate score predictions. It also explores fairness-unaware models, like ListNet, and their variants. The authors consider various strategies for generating input rankings, including using inferred or hidden protected attributes, and evaluate their performance. The paper concludes by discussing inference services for missing protected attributes, such as behind the name and gender API, which are used to evaluate the accuracy of inferred demographic attributes. This research paper delves into the critical issue of fairness and utility in ranking systems, particularly when demographic inference is involved. The authors employ various metrics to assess rank fairness, including skew, NDKL, and exposure ratio, as well as utility metrics like NDCG. They utilize real-world datasets, such as Law, NBA, WNBA, Compass, and Boston Marathon, to train and test their models. The authors leverage demographic inference services, including NAMSR, to deduce sex from names. They acknowledge that these services may return unknown values for certain names, which are then assigned to the disadvantaged group. The authors employ fairness-aware and fairness-unaware models, trained with and without protected attributes, to analyze the impact of demographic inference errors on fairness and utility. In their controlled study, the authors systematically vary the level of errors in the protected attributes, mimicking common errors in demographic inference. They consider bidirectional and unidirectional errors, where candidates are incorrectly inferred as belonging to a different group. The authors compute fairness metrics using ground truth labels and average over all error levels. In their case studies, the authors use popular inference methods on real-world datasets, evaluating the accuracy of each inference service. They find that NAMSR has the highest number of unknown values, while Gender API has the lowest. When considering accuracy for identified items, NAMSR performs best. The authors highlight the importance of handling unrecognized names, as these can affect fairness and utility metrics. They assign unrecognized names to the disadvantaged group to prevent misclassification. The authors then measure fairness and utility metrics, using ground truth sex attributes and judgment scores, to analyze the effect of wrong demographic inference on fairness-aware algorithms. The authors present an evaluation of various fairness strategies in ranking systems, focusing on the impact of inference errors on fairness and utility. They use 4 real-world datasets, including Law, W, NBA, Compass, and Boston Marathon, each with its own protected attribute and disadvantaged group designation. The authors first present the statistics of the training and test data, including the size of each dataset, the proportion of males and females, and the attribute used for inference. They then evaluate the performance of various inference services, including Gender API, Behind the Name, and NAMSR, in terms of correctness and error rates. The authors then present the results of their experiments, which involve applying controlled inferencing processes to infer protected attributes. They evaluate the fairness and utility of various fairness strategies, including oblivious, LTR, hidden, failure, and oblivious plus phi RRR, using metrics such as DADV, ADVA exposure ratio, NDKL, and NDCG at 100. The results show that oblivious consistently has a DADV, ADVA exposure ratio farther from 1.0 than the fair interventions, indicating that it does not explicitly optimize fairness. However, it yields similar DADV, ADVA exposure ratio values to hidden, showing that hiding the protected attribute during testing would yield fairness levels similar to those when the protected attribute is not used during training. The authors also find that LTR's DADV, ADVA exposure ratio rises with inference error across all datasets, while FAIR-LTR's DADV, ADVA exposure ratio decreases with error rate. HIDDEN's NDKL values are consistently outperformed by all fairness strategies for up to 1,520% inference error rates. The results also highlight the trade-off between fairness and utility, with oblivious plus phi RRR showing a decrease in DADV, ADVA exposure ratio and an increase in NDCG at 100 as the inference error rate increases. Overall, the authors demonstrate the importance of considering inference errors when evaluating fairness strategies in ranking systems and provide insights into the performance of various fairness strategies under different error rates. The research paper examines the impact of errors in inferring protected attributes on fairness and utility metrics in ranking systems. It focuses on various LTR-based ranking systems that instill fairness at different stages, such as fair LTR models or a posteriori by using a fair re-ranker. The study highlights that in scenarios with high inference error rates, fairness models requiring protected attributes may inadvertently lead to the advantaged group having lower exposure than the disadvantaged group. The paper also explores whether to hide or infer protected features if they are not readily available, observing that wrong inference can improve fairness in certain cases. However, it emphasizes the dangers of demographic inference for practitioners and suggests that if inference is deemed necessary, fair re-ranking solutions serve as a more resilient alternative. The study concludes by discussing ethical considerations in using demographic inference tools, highlighting the need for continuous monitoring of fairness performance and the assessment of unintended consequences. The paper discusses the issue of fairness in learning to rank models, focusing on the problem of disparate exposure. It presents a fairness-aware learning to rank model that aims to reduce both ranking errors and disparate exposure between two groups. The model is trained with protected attributes and uses a scoring function based on these attributes. The paper compares different fairness-aware models, including DELTR and det constsort, and evaluates their performance on various datasets. It also provides details on the parameters used for DELTR and det constsort, as well as trade-off graphs for the NBA dataset. The authors present NDCG plots at different cutoffs for the first simulation scenario and real-world use case experiments, comparing the performance of various fairness-aware models. The paper addresses the issue of fairness in learning to rank models and presents a fairness-aware model that aims to reduce both ranking errors and disparate exposure. It evaluates the performance of different fairness-aware models on various datasets and provides insights into the trade-off between fairness and utility. The research paper presents a comprehensive analysis of various ranking strategies for enhancing fairness in search results. It introduces the concept of fairness-aware ranking, which aims to balance the visibility of different groups within a search result. The authors propose several models, including LTR, fair LTR, LTR fair RR, hidden fair RR, and oblivious fair RR, each with its own strengths and limitations. The paper discusses the importance of considering both relevance and fairness in search results, highlighting the trade-off between these two objectives. The authors use NDKL and NDCG and 100 as metrics to evaluate the performance of their proposed models. The results show that while LTR and fair LTR models perform well in terms of relevance, they lack fairness. On the other hand, LTR fair RR and hidden fair RR models achieve better fairness but compromise on relevance. The oblivious fair RR model is found to be the most effective in balancing both relevance and fairness. The paper also explores the impact of different error rates on the performance of these models, demonstrating that as the error rate increases, the trade-off between relevance and fairness becomes more pronounced.